much, Andy. So I've been tasked with giving a brief overview about some of the opportunities in New Zealand, and particularly I'm going to focus on the Hikurangi subduction zone and talk a little bit about the tectonic setting for those of you that are not that familiar with New Zealand, some scientific questions that various projects are trying to address at the moment, and opportunities for collaboration. Because it's a really short format, what I did is I started to make a kind of literature review, a list of some of the relevant papers, which I believe Andy has posted on this site somewhere. So you might want to look out for that if you want more information about individual science projects. So just to recap for those of you that are not familiar with New Zealand's on a plate boundary, and as such it's a great place to study subduction. And because of the fact that it sits between the Australian and the Pacific plates, and the nature of the lithosphere of both these plates changes from north to south, that creates a variety of tectonic environments. Now, hang on, there we go. As well as the Hikurangi subduction zone, which is offshore North Island, there is an associated back arc or intra arc, the Taupo volcanic zone on land, which produces is the most productive rhyolitic system on Earth. And there's another subduction zone, which is down the bottom of the South Island, and that's a nascent or juvenile subduction zone. So that's a great place to study subduction initiation. And as well as that, there's a continuation of the Hikurangi and Taupo subduction system to the north into the Kermadec Arc and the Havre Trough. But I'm going to focus today on the Hikurangi margin. So this is a beautiful perspective view put out by the guys from NIWA, and it shows some of the main features. And one of the unique things about Hikurangi that makes it so great to study subduction is that the oceanic crust that's being subducted there is a little anomalous. It's quite buoyant because it's it's a large igneous province, the Hikurangi Plateau, and because it's so buoyant, that means that a lot of the forearc is actually exposed onshore. And that means that onshore instrumentation is not that far away from the trench. So in New Zealand, we have a collaborative project between GNS Science and funded by the Earthquake Commission of New Zealand called GeoNat, and that has a lot of seismographic sites and continuous GPS as well as other things onshore. So we already have a sort of mini subduction zone observatory in New Zealand. One thing you'll also note, and another feature of the Hikurangi subduction margin, is the incredible change in the morphology of the wedge from north to south. So in the north, it has a very steep frontal taper, and you can see these scars, which are believed to be where seamounts have been subducted beneath the wedge. Whereas in the center and the south of Hikurangi, the accretionary wedge is much broader and lower tapered. And some of that change may have to do with changes in the plateau thickness from north to south, and also the fact that most of the sediment is being dumped into the Hikurangi channel, which runs just outboard of the accretionary wedge. And so there's a change in the amount of sediment entering the subduction zone. There is another huge change that's Longstrike, and it's not totally sure yet how this relates to all the other changes, and that has been seen in the present-day deformation field. So campaign GPS and continuous GPS in the North Island has shown that, in fact, the forearc is rotating relative to stable Australian plate clockwise, partly because of the Taupo rift, which is essentially detaching it from the rest of the Australian plate. And the short-term GPS signal, when inverted for locking along the subduction interface, shows this huge change from north to south. So in the north, the subduction interface is mostly creeping to very shallow depths, whereas in the south, and this is the red zone is showing locking along the interface, it's locked down to depths of about 30 to 35 kilometers. And this change is also mirrored in observed slow slip episodes. So in the north, the slow slip episodes, which are of short duration and occur fairly frequently, are very shallow, whereas in the south they're much deeper and they have a longer recurrence interval and longer duration. In fact, a recent paper by Laura Wallace and others used offshore pressure gauges, so seafloor geodesy essentially, to show that during one of these slow slip events, there may actually have been slip all the way out to the trench in the north. So this gives an unprecedented opportunity to study slow slip in a setting where it's occurring very close to the Earth's surface. So as well as the change in the locking depth shown here, the change in the wedge morphology, there are a bunch of other changes along strike, and one of the main science focuses at the moment is trying to understand how these are all related. So for example, the change in incoming sediment thickness from north to south, the onshore fluid chemistry suggests more of an involvement from the subducting slab in the north and the south, and there's a lot of geophysical evidence that also shows changes. New Zealand also has a really good 2D seismic offshore active source seismic network, so some of it's shown here, and that has shown things like subduction of seamounts, highly reflective zones that are roughly coincident with some of the northern shallow slow slip zones, so maybe related to fluids, incredible wedge structure and prothrust zone, and also some of the deeper seismic refraction studies that have shown anomalous velocities at depths that may indicate underplating sediment as well. There's also a really good source of information about seismic tomography. So there's a 3D New Zealand model that's been put out by Donna Aberhart-Phillips, Martin Raynor, Stephen Bannister and others, and that's accessible. And a good recent updated model of the subduction interface at depth. So if you put those together, you can start to think about different changing properties along the interface from north to south, and that does show that there are changes. There's anomalously high VPVS in the north, for example. There's also an onshore magnetotellurics data set that's been developed here at GNS, and that also shows intriguing changes in electrical conductivity from the north to the south. And one other thing, of course, that New Zealanders are particularly interested in is what the seismic hazard is from a potentially large megathrust event on the Hikurangi interface. And because of the short historic record in New Zealand, we don't actually have a historical record of this. So the paleoseismologists are hard at work trying to piece together all the evidence onshore from co-seismic subsidence or tsunamis. And they've recently published a paper that shows the first direct evidence for large ruptures, interface ruptures in southern Hikurangi. And they're still working on tying that together with segmentation along the margin. So what we're trying to understand is how large a rupture could occur along this subduction interface at the same time. And hopefully that will also be moving offshore fairly soon as well. So I just want to close by listing some of the funded projects right now that are going on. There's some really exciting science going on. Of course, there's this riserless drilling, which has been scheduled for IODP drilling, scheduled for early 2018. And the main targets of that is these shallow slow slip patches offshore Gisborne in northern Hikurangi, and the black stars here show some of the potential drilling sites. There's one outboard of the accretionary wedge to get a kind of input section and understand the sediment that's going in, but there'll also be downhole logs and observatories as part of that. And there's a synergistic 3D seismic survey that's going ahead just before that which Nathan Bangs is one of the PIs on, and he's here today, so he can talk more about this. But the idea is to get some 3D seismic data around the drill sites. So Nathan, I'm not sure if your microphone's working. Do you want to say anything on that?
Can you hear me?
Yep.
Susan?
Yep.
You can hear me, okay. Yeah, I can say a few things about the 3D survey. We'll be collecting the data on the line sets, as you can see in the figure, and that will happen in probably January of 2018, just sort of in between the LWD leg and the main drilling leg for New Zealand. And we'll survey about a 15 by 60 kilometer area that will cover good portions of the slip area that was defined by the ocean bottom pressure gauges, as Susan mentioned a minute ago. You can see the contours on the map on the left there and the outline of the 3D box. So we'll cover a good bit of that slip area, and we're looking for how much sediment is being subducted, so where the plate interface is and what sediments are going down that may be bringing substantial amounts of fluids that interact along the plate interface, and help controlling some of the slip activity. And we'll be looking at some of the reflective character of the plate interface itself, and see how it varies as you go deeper and into the areas of active slow slip. And then we'll also look at some of the structure of the overriding plate in 3D. This is a complex setting with lots of deformational structures, and the 3D data hopefully will clarify a lot of the upper plate structures as well, to look at where fluids may be venting from or migrating along, and some of the deformational properties of the upper plate. Also, you can see those, I think those little red dots inside the 3D box there are locations of OBSs that we'll be deploying. There will be hopefully 92 OBSs that will record our shots from the survey, and these will be analyzed by a group in the UK led up by Rebecca Bell to do full waveform inversion and get very detailed high-resolution velocity maps of the structure that will help do some similar, achieve some similar. I should also mention there's going to be what's called the Shire project, which is a long offset OBS refraction survey. Yes?
You're breaking up a little bit. I think yep.
Okay, you can go on then.
Okay, thanks, Nathan. That's great. So, yeah, just to finish up with a few more funded projects. Those of us in New Zealand are very excited because we've just received news that we've got funding through the government for $6.5 million New Zealand dollars over the next 5 years. And this is funding some of the New Zealand scientists' research time to participate in all these international projects and to do some more paleoseismology, some numerical modeling, more rolling seafloor geodesy, and generally science in support of the drilling and active source surveys. So that's really good news for us. Should also mention the Hobbits NSF project, which is some way through right now, and the acoustic pressure gauge data mentioned earlier has already been published, and that's really exciting. There's also some seismological analyses going on of OBS data that's in progress for that project. And here in New Zealand, Bill Fry has got a master in funding to look at seismology of shallow slow slip zones. So the figures down the bottom, the one on the left is showing some of the planned sampling as part of this MB proposal, both onshore and offshore, to try and increase our knowledge of previous ruptures along the margin. So that's really exciting. And then there's a sample image from the OBS data from Hobbits from Erin Todd, showing some of the pics of seismicity that she's working on. All right. Yeah, so that was focusing more on the slow slip, analyzing slow slip, but there's also a bunch of projects which is looking at the changes in megathrust behavior along strike And part of the AMBI fund I mentioned before is looking at that, the paleoseismological part. There's also this NSF project in the Integrated Earth Systems called SHIRE, with Kirk McIntosh as PI, and that involves active source transects, as Nathan just mentioned, across and along strikes. So some of these lines are shown in the bottom left diagram. It also involves more paleoseismology and fluid mechanical modelling as well, which I'm working on with Damien Saffer. And I just wanted to mention the land-based magnetotellurics that GNS is doing again, because they're really keen to collaborate with people from overseas on maybe extending this to offshore. But this plot on the right shows some of their collected data so far. So they've been targeting this region where the locking zone changes from shallow to deep to try to understand if there's what the changes in the conductivity are across that. There's also an NSF-funded project to look, or several actually, to look at time-dependent inversions of slow slip to see how they migrate along the interface. And Yoshi Kaneko has a Marsden using full waveform inversion to look at the megathrust as well. Right, and the other cool thing is because the forearc is part of it is exposed, is that some of the fluid chemistry on shore can give us information about the subduction interface. And there's a bunch of projects on that. Agnes Reyes is writing a big compilation paper at the moment, looking at the changes from north to south and the fact that there seems to be more subducting slab component in the north and the south. There's also much higher flow rates in the north. And Jamie Barnes has a NSF proposal that she's working on, looking at fluid, mobile and volatile elements, also on shore. And Sean Barker from Waikato is collaborating with Jamie, but he's also been trying to detect if there's changes in fluid chemistry and flow associated with some of the shallow slow slip events in northern Hikurangi. Some of us are trying to put some of this fluid chemistry information and what it means into fluid mechanical models as well. So just to finish up, there's many potential New Zealand partners to work with in New Zealand. There's a GeoNet network which you can access the data from, which is a great resource. The New Zealand Earthquake Commission and government fund a lot of New Zealand participation in the science. So the main researchers are located at GNS, Science, NIWA and the universities. And there's also a thing called the East Coast Lab, Life at the Boundary, which is a sort of consortium between government, regional councils and interested stakeholders along the East Coast to try to bring them all together and communicate, and especially communicate with public about all the science that's going on. So that's also a very good resource. So I'll leave it there with just the main key science questions that a lot of us are trying to address in Hikurangi, and just to say it's a great place to do subduction science.
All right, thanks, Susan. So I'll let those sit there for a second, and people can think about those. And then we're going to pivot over to our next two speakers in Japan. So we'll start off with Yoshi Ito-san. So Yoshi, I will have that prompted on your screen in just a second to share it. 1 second.
Okay.
Okay.
What? Okay.
It's okay. We also see your slide presentation screen, but I think that's okay. I think you can go ahead.
Okay. Great. I think good morning, everyone. Or good evening, or good afternoon. Okay.
Maybe 1 second. Yoshi, your microphone is a little ragged. Yeah, I'm having a very hard time hearing you, actually.
Okay. Just
Maybe we want to move over to Tamura-san while Yoshi troubleshoots that. I think let's do
Hello.
that.
Hello. Can you hear me?
Who is speaking?
Yes. Can you hear me?
Yes.
Okay. Can I
Okay, I
start?
think that's much better. Why don't you keep going then?
Okay. I will start. Okay. Now, today I'd like to try to introduce recent Japanese project and related science which are probably all of them are related to the future subduction zone observatory, I guess. Okay. Okay. First of all, I'd like to brief introduction of Japanese subduction zone. So as you know, in Japan, two plates are subducting beneath the landward plate. One is a Pacific plate with conversion speed with 8 centimeter per year, and the other one is Philippine Sea plate with conversion plate speed with 4 centimeter per year. Due to this two kind of subductions, we have several phenomena could be observed. This is not only seismology or geophysical phenomena, but also geological and volcanic and petrological very interesting phenomena as well. And especially due to this subduction, uh, on this talk, I'd like to focus on the two subduction zones, especially Japan Trench here and Nankai Trough. As you know, in Japan Trench, we had a great earthquake in 2011, and due to after this big great megastructure earthquake, we have started a related big project related to this earthquake. And if we look at the Nankai Trough, we also have several interesting phenomena, which are called as throw earthquakes. We also have a big project related to investigate this throw earthquakes. Yes, and okay. So first, I'd like to introduce a big project related to IODP drilling project. This is called as a Kaname project. This lead proponent is Gaku Kimura, and during this project was already done, but this project has many products related to the understanding of the megastructure earthquake and related phenomena. During this project, we did understanding overall framework of Nankai Trough subduction zone by using a drilling project or through the drilling project. We try to revealing materials and mechanical and hydrological properties of seismologic faults. We also constructed and verified a comprehensive model for play and seismic process. So this is not only related to the megastructure earthquake, but also we also focused on tremor activity or throw earthquakes. And this Kaname project has already done, but Gaksan got the huge budget from the Kakenhi. So this new project is just started last year, and this Kakenhi is also focused on the Nankai area through the drilling project. And especially this project, they are trying to evaluate the hazard of future megathrust earthquake in the Nankai Trunk. Okay, next one is the other big project. It is which ongoing project in the Japan Trench. As you know, in Japan Trench, we had a large earthquake in 2011. Before and after the earthquake, we successfully observed the very, very interesting phenomena. This is not only co-seismic slip, but also through earthquake before and after the earthquake. If you look at the before the earthquake, we also observed the tremor or slow slip event around the megathrust area. I introduced a little bit this one in the next slide, and we also we also observed the post-seismic deformation. This is not only related to the after slip, but also viscoelastic rebound due to the mega slip around the seismic area. So after this figure showing the seismic surveys data, which are done after the earthquake. If you look at figure, we found out very, very interesting structure, and this structure was interpreted as related to the megathrust earthquake in the 2011 Tohoku earthquake. And this typical structure is very, very related to the megathrust earthquake near the trench or slip to the trench. If we found this kind of similar structure, not only a huge co-seismic area in the 2011, but also if we found out, for example, northern part or southern part area, this is one evidence to show the past, the previous large or megathrust earthquake near the trench along the Japan Trench. So to investigate such kind of issue, Ryota Hino, Tohoku University, got a huge budget from Japanese government. On this project, we are focused on liberating past shallow seismic strip, especially shallow seismic strip, and information from high resolution seismic survey, for example, these kind of seismic survey data. And we also focused on the investigation past megastrip event from tsunami turbidite layers based on the core sampling with such as a piston coring or a drilling project from ultra deep piston coring or deep piston coring system near the Japan Trench. We also try to identify past seismic deformation process on the shallow fault by using the dense array of broadband seismic and geodetic sensors, which are distributed around here. On this arrays, we also try to make array of seismometer to identify the tremor or possible tremor activity after the earthquake as well. And we also have the other big project, which are focused on the outer rise earthquake. After the earthquake, we very, very worry about the occurrence of the large outer rise earthquake, which are very, very related to the tsunami disaster in near future, of course. Kodaira-san, Shuichi Kodaira, Jamstech proposed to investigate such kind to mapping of potential faults of outer rise earthquake by using this kind of seismic survey. And this is also funded, and this project was started from last year. and continue during 5-year both project. Okay, next one is also related to the big project. This is this is especially focused on the slow earthquakes. On this project, this project lead proponent is Kazushige Obara, ERI, University of Tokyo. On this project, we will focus on the mainly slow earthquakes, especially to understand the true physics of or what's control of slow earthquakes. During this project, we'd like to try to understand shift to the discovery of slow earthquake to the understanding of slow earthquakes. And we also, during this project, we try to do shift to the regional understanding to general understanding. On this project, one of the future of this project is this committee is not only from the geophysics and geology, but also we have attendee from the physics. To collaborate in these three fields, geophysics and physics and geology, we try to totally understand of slow earthquakes phenomena. Okay. Okay, I move on to several scientific questions and new opportunity during this kind of large project. So my main scientific question is what's control on the fast and slow rupture mode, especially shallow portion, such as Japan Trench as well as the Nankai Trough. During after the before or after just 2011 Tohoku earthquake, we successfully observed several mode of rupture along the Japan Trench, especially shallow portion. If we look at the Japan Trench, we also observed periodic slow slip event in the Japan Trench, and also we also observed the slow slip event, which are prior to the 2011 large earthquakes, and also we also observed the slow slip event with migrating speed or migration speed, or this is probably related to rupture speed of slow earthquakes with a speed of 2 km per day or 5 km per day in the before the almost 1 month. And also, if we look at just before the main shock, we also observe more fast propagation very, very close to the occurrence of the 2011 Tohoku earthquake. We need to understand this kind of variation of migration speed through the slow slip to fast rupture or main shock. Also, so we need to understand what controls the migration speed or rupture speed on the subduction zone, especially shallow portion. So we also, as you know, after the earthquake, Japanese government decide to deploy the cable system to observe the tsunami or seismicity along the Japan Trench, and as well as DoNet, Nankai Trough. Actually, DoNet in Nankai Trough had started before the 2011 Tohoku earthquake, and now we also have this kind of networks as well as ocean bottom geodesy or GPS acoustic survey, which are distributed by the Japan Coast Guard, shown by this red dot. So in near future, we can use this kind of data to monitor the slow earthquakes as well as the seismicity or usual earthquake. But we need to consider how do we evaluate real-time monitoring data to mitigate earthquake and tsunami disasters by using this kind of networks. Okay, I'll show potential partners and international collaborators shown here. JAMSTEC or National Research Institute or for Earth Science and Disaster Resilience, NID, and National Institute of Advancing Industrial Science and Technology, ICE, or Japan Coast Guard, and Japan Meteorological Agency, or Geospatial Information Authority of Japan as well. And I'm not sure here of Japanese university. Of course, Japanese university are very, very strong potential partners in Subduction Observatory in future. Okay, I'll show my question for attendee of this webinar. Shown here. Oh, thank you. Thank you. That's all.
Thanks, Yoshi. So again, we have some questions for the you out there in the audience to think about, and I'm going to pivot over to Tomura-san to give the last talk of the webinar today. So Yoshi, Tomura, you'll see that in just a second on your screen.
Could you see my screen?
Looks good.
Okay. Shall I start?
Sure.
Yeah, I will talk about crust mantle connections from Izu-Ogasawara and Aleutian arcs to Kermadec arc. And this talk is based on our study of our study entitled Advent of Continents, New Hypothesis, which will be published in scientific report soon. And this is the Izu-Ogasawara arc, which are produced by subduction of Pacific plate beneath Izu-Ogasawara arc. And we can separate Izu-Ogasawara arc into northern segment and southern segment. This is the crustal structure by Kodaira et al. 2007. You can see the northern segment have thick crust, about 30 kilometer thickness, compared to the thin crust of the northern southern segment. And this is the crustal thickness and water depth from north to south in Izu-Ogasawara arc. Again, northern segment have shallow water depth and thick crust, 30 kilometer thick around here. But southern segment have a very deep water depth and thin crust. This is about 10 kilometer thickness and 20 kilometer. So based on isostasy, you can see the depth of water between arc front volcanoes. And this is the crustal thickness. And there is a good correlation between this water depth and the crustal thickness. Northern segment is shallow water depth and thick crust, and southern segment have a large water depth and thin crust. And this is Aleutian arc. This is bathymetric features of Aleutian arc system. So this is the topographic profile along these red lines. And in the Aleutian, this Adak Island, and east of Adak, the water depth is fairly shallow, and we have many volcanoes. And west of Adak, the water depth between volcanoes become much deeper, and these are submarine volcanoes. So we can estimate the crustal thickness in the allusion based on these diagrams. East of Adak, there is seismic study which showed the crustal thickness about 35 to 37 kilometer, and water depth is less than 500 meter. So this is very consistent to this is Ogasawara arc here. And west of Adak, the crustal thickness is not independently known. However, it could be similar to the thickness beneath the southern segment of East Ogasawara arc, which is about 10 to 20 kilometers thick, because the water depth of west of Adak and is similar to southern segment of East Ogasawara arc. And this is magma types. Interestingly, the volcanoes on thin crust produce andesite. This is northern segment of East Ogasawara arc. These are silica content, and these are basalt, andesites, and dacite rhyolites. Northern segment and east of Adak, we have dominant products. Dominant products are basalt. But southern segment of East Ogasawara arc and west of Adak, the andesite magmas are dominant products from these areas. So thin crust produce andesite and thick crust produce basalt. This is schematic illustration of the effect of pressure on forsterite N-type equilibrium in the hydrous environment. Primary magma in equilibrium with mantle peridotite become progressively more silica-rich with decreasing depth. At high pressure in hydrous conditions, congruent melting of orthopyroxene results in primary basalt melt. So at high pressure, we can make only basalt in the mantle. But at lower pressure and also in hydrous conditions, N-statite melts incongruently to produce primary andesite melt. So primary andesite can only be produced when the pressure is low. So this is the cartoon which shows the contrast between thin crust and thick crust. And we think the mantle source, magma source of mantle wedge is rising mantle diapirs. So these mantle diapirs store near the base of the oceanic crust at depth controlled by the thickness of the overlying crust. Where the crust is thin, like southern segment of East Ogasawara arc, west of Adak, and maybe early Earth, melting occurs at relatively low pressure in the mantle wedge, producing andesitic magmas. And where the crust is thick, like northern segment of East Ogasawara arc and east of Adak, melting pressure are higher and only basaltic magmas tend to be produced. So this is the conclusion from East Ogasawara arc and Aleutian arc. Shallow mantle melting in hydrous conditions is crucial for the genesis of andesitic magmas, thus the genesis of continents. So andesite is produced only when the crust is thin, thus only in oceanic arcs. If so, most andesite magmas erupted on continental crust, like Northeast Japan or New Zealand, could be recycled from primary andesite previously produced in oceanic arcs. The rate of continental crust accumulation might have been greatest early in Earth history when subduction was initiated and if the initial crust was thin. And this is Kermadec arc, volcanic front, again bathymetric features of the Kermadec arc system. And this is from A to B along volcanic front of Kermadec arc. And from A to B, Kermadec arc also divided in northern segment and southern segment. Northern segment have shallow water depth because these volcanoes are on the Kelmatic ridge. But in the southern segment, water depth is about 3,000 meters, very deep, because the Kelmatic ridge is east of volcanic front. So southern segment is similar to west of Adak or southern segment of Izu-Ogasawara Arc. And northern segment is similar to northern segment of the Izu-Ogasawara Arc or east of Adak. So this is very simple relationship between depth of water between arc front volcanoes and crustal thickness. And these are from Izu-Ogasawara Arc. And Kelmatic southern segment, water depth is about 3 kilometers. So the crustal thickness could be about 15 kilometers, which is much thinner compared to the northern segment of the Kelmatic arc, which could be about 30 kilometers thick. So what's the difference of magma types between northern and southern segment of the Kelmatic arc? We have Vickers cruise by Lloyd. PI is Kai Horn from March 1st to April 15, 2017. And Kai will talk about this cruise in the workshop. And this is the real best opportunity to compare the arc volcanoes of northern segment, which have thick crust, and southern segment, which have thin crust. And again, we expect the continental crust, which is andesitic in composition, only be produced in the southern segment of the Kelmatic arc. But in the northern segment, the pre-existing continental crust should be melted by basaltic magmas. Okay, thank you very much.
All right, thank you all for the presentations. So I think we had some initial sort of questions for the audience earlier regarding some of the science that's presented here in the context of the SCO workshop. In the other webinars, some of the general questions have been, what are the most compelling science opportunities for an SCO? What are the capabilities, data sets, and infrastructure that are needed? And what sort of partnerships, both international as well as within places like the United States, would be needed to make something like this happen? So I would encourage folks in the audience to submit questions either related to those or related to any specifics that you saw in the presentations right now. And I have one that I can read off the top, and this is a question from Karen Lloyd, and was related to the most recent presentation by Tamura-san. Karen asks, why does water depth negatively correlate with crustal thickness? Is it due to the barometric pressure of water or the sedimentation rate of the water?
Based on isostasy, crust have low density compared to mantle. So if the crust is thick, the water depth should be shallow, and the thickness itself become thicker. And this is based on isostasy, which we expect from the difference of density between crust and mantle.
Okay, thank you. We'll give people a moment to type questions in. I don't have any queued up immediately. Okay, here's one from Jeff McGuire. So Jeff asks, in Japan, there is a spectacular amount of work going on. What types of higher level integration efforts have been most successful at combining the results of individual research projects into higher level system models?
Yes, probably this. Can you hear me?
Yes.
Yes, could you tell me this is a very, very general question, I guess. Uh, we need to more focus on the topic. Yeah, uh, yeah, generally speaking, in Japanese community, like to uh, uh, focused on the subduction zone science. This is not only from the effort from the geophysical community, as well as geological community and physics community. Now we are trying, especially a slow earthquakes science of slow earthquakes in a big project organized by Obara-san. This is now ongoing project. Yes, actually, this now ongoing project. Yeah, that's all. It's enough for my answer.
Jeff also mentioned, he said, for instance, you mentioned work with physicists on slow earthquakes, or similarly something like SCEC, the Southern California Earthquake Center.
Yes, okay, thank you. Yeah, from now I'm just only focused on the slow earthquake science or mega thrust earthquake related to the Nankai Trough and Japan Trench. We try to integrate all of knowledge or all of effort from the other fields as well as seismology or geophysics now. So, how about the Tamura-san? Do you have some information for integrated science in volcanology or petrology? Tamura-san?
Yes, yeah, I'm thinking about this now. Actually, we had some international workshop of international crews compared to Japan, to New Zealand, and other areas. But at the moment, it didn't work from Japan side. But from Germany, the zone will have dredge crews in Kermadec, so that's a great opportunity. And your question is some integration in Japan, for Japan, or like this?
Yes, yes, that's right. Yeah. If you have some this integrated science in your field, yeah, you have, right?
Yeah, actually, JAMSEC have both geologists, petrologists, and geophysics. So the geophysicists. So we often talk with Kodara-san and Obana-san and geophysicists in JAMSEC. So that's a good place to have some idea which combine from petrology and the geophysical side of these areas of Isbonin, Kermadec, and New Zealand.
Okay, thank you.
Okay, great. So I have a question/comment from Nicholas Haman. And Nick says, nice presentations. I am going to contribute a white paper generally promoting deep submergence applications, so ROVs, HOVs, AUVs, etc. Japan has had a lot of good trench slope work done in this mode. Kaiko, Shinkai 6500 along Nankai and elsewhere. But are there equivalent plans or previously work done on this in the Hikurangi subduction area?
Hi, it's Susan here. I'm no expert on that, but Cornell Dewar, New Zealand, has been doing some submersible work, especially I think in the offshore to the north of Hikurangi and Kermadec. So he would be the person to ask that question, but I don't know if he's part of this webinar. Yeah, sorry, I don't have any knowledge of that. So maybe Laura can comment. She's also in the webinar.
If there's a comment coming from that, I'll look out for it. There's another question for you, Susan. It's from Adam Holt. And Adam asks, is there a seismicity signal, such as down dip extension / normal falls associated with the subducted portion of the boundary between LIP and the regular oceanic plate? Or is the buoyancy thickness contrast not significant enough to observe or expect that?
Yes, I believe there is, and there's a few papers that talk about that from the tomography group here at GNS, so Martin Raynor's in particular, and in that reading list, I think I've put some of his papers where they see both a change in the velocity structure at depth and a change in seismicity that they associate with the extent of the plateau that's been subducted. So you might want to check out those references.
And this is a good point to mention. I will be putting those references along with the PowerPoints that I can post today up on the website either later today, tonight, or early tomorrow. So those will be available shortly, and then the webinar will go up next week once Yoshi's paper clears its embargo for the figures.
And just a point that those of you that work on Hikurangi stuff, I just started putting this list of references together 2 days ago, so there's bound to be some things missing, and maybe it would be a useful thing to keep something going, updating it with recent papers and things I might have missed, so that people can have somewhere to go to get an idea of what they should read if they're upskilling themselves on Hikurangi.
Great. And Laura Wallace did respond on the ROV question, and she mentions there is an ROV expedition planned to download IODP observations at North Hikurangi probably around 2022 or so. It could make sense for people to submit proposals to utilize the ROV for other research purposes around that same time. So, you know, that's there's a good lead time notice for that. Question, I think this is pivoting back to Japan. This is from Donna Blackman, and Donna asks, perhaps a question that is answerable now is how many years do you think it will be until it is clear whether an integrated slow slip project will make a difference in terms of science understanding?
Yes, slow slip science project is actually a 5 years project. It just started this year.
Okay. Well, that was. I'm going to give people another chance to type in any remaining questions. That was the last one I had in the hopper for now. So maybe we'll just pause for a second, see if anything else comes in. I'll give you guys, while that's happening, does anybody have any concluding remarks that they want to make? No pressure.
It's really awesome subduction science going on in Japan and New Zealand, and it's really exciting. And I think one thing maybe we haven't talked that much about is the comparison between different subduction zones and different subduction settings, but I think that gives us really important clues sometimes as to what the major controls are on some of the physics behind things like slow slip and other phenomena.
The other thing that I could add is that if there are more questions or more issues that you'd like to have brought up into whatever we present at the Subduction Zone Observatory, I think you should email them to one of us, and we can share them with each other and come up with some answers. in preparation for our presentation at the Subduction Zone Observatory workshop.
Okay, well, in the absence of any more questions, I'll encourage anybody who has any more that come up later, please email them to our presenters. As Nathan said, there'll be opportunity to synthesize this at the workshop. And thank you all for attending. Thank you especially to all our presenters for getting up very early to do this. I think everybody associated with the workshop really appreciates it. And as somebody who does a lot of these webinars, I really appreciate it too. So great presentations, and one more webinar tomorrow at 3 p.m. Eastern on on Mexico, Central America, and South America subduction zones. So I hope to see some of you all then.